Debbie Anderson, a researcher in the Department of Linguistics at UC Berkeley, and I run the Script Encoding Initiative, or SEI. I'll give a brief background on the project, and my talk will be followed by two presentations, both by people who work on the project, one by Charles or Chuck Riley of Yale University Library, who will talk about African scripts, and his talk will be followed by Anshuman Pandey, who will talk about his work on historic scripts. The Script Encoding Initiative project is based in the Department of Linguistics at UC Berkeley. The goal of the project is to help get various scripts into the Unicode standard, which is the first critical step needed for users of modern and historic scripts to be able to access the scripts on computers and devices. Since its inception in 2002, the project has helped get over 90 scripts into Unicode, many of which involve my co-presenters. So what does SEI do? The project works with user communities to get Unicode proposals written. This may include enlisting veteran proposal authors, such as Anshuman Pandey, to write a proposal. Scholars on the historic Proto-Elamite script, for example, required help on a proposal, so Anshuman Pandey has taken the lead on the proposal authoring. Work necessarily entails working closely with communities in gathering information, locating people with knowledge of the script. Chuck Riley, who has extensive contacts with various communities in Africa, has been invaluable in this effort, and he's shown on this slide. SEI gets Unicode proposals reviewed by scholars and users, as well as Unicode experts, answering such questions as, is the proposal accurate, and is more technical information needed? Finally, SEI shepherds proposals through the two standards committees, so scripts get approved and published. One new direction for the project has been to assist user communities in the steps after a script is in Unicode, namely getting Unicode-based fonts and keyboards created, and getting the script supported in operating system and apps. Work on fonts has been aided by collaboration between SEI and the Google Nojo project, as well as the ANRT project in France. To help communities understand more fully the steps involved in getting their script available on devices, SEI has been participating in the Translation Commons project, which has developed a guide geared for communities called Zero to Digital. This guide describes how communities can enable their script and language digitally on devices and where to turn to for help. Unicode today contains 154 scripts, including the Hmong script, which was published in March 2020. However, over 140 scripts are not in Unicode. The SEI website lists the various unencoded scripts, and I provide a link to the web page on this slide. The scripts that are not encoded typically need in-depth research, as they're not generally well known, or they have features that present complex challenges in the encoding. The list of unencoded scripts falls roughly into three different groups. Recently created scripts, that is, those created in the latter half of the 20th century or early 21st century and still being used. Near modern scripts, which include scripts that date to the 19th to 20th centuries but are no longer used. And historical scripts. Each presents its own set of issues. For recently created scripts, one difficulty is the fact the scripts may not yet be fully stable and may still be in flux. Often communities are very anxious to get their script into Unicode so they can use it and can gain currency, but the script may still be developing and there may not be a single agreed upon set of characters, particularly if the user communities are widely dispersed. The Berea script of Sudan and Chad is such a case. A number of scripts that have been described as near modern may be lacking anyone who remembers the script, or a dearth of written materials that make it difficult to get all the needed information for a Unicode proposal. This is true for the Wolai script of the Caroline Islands in Micronesia. For the historical scripts, pinning down the repertoire can be a challenge, especially for those that are not fully deciphered. Also, some scripts pose complex encoding issues, such as the Mayan hieroglyphs. So to sum up my portion of this presentation, SAI has had really good success in getting scripts into Unicode, but many more are left to do. At this point, I'll turn it over to Chuck Riley, who will describe the situation with the scripts of Africa.
Thank you, Debbie. My name is Charles Riley. I'm the Catalog Librarian for African Languages at Yale University Library and CEO of Athinkra LLC. The paper that I will talk about today is entitled Taha Jaha, Advances in Encoding and Implementation of West African Scripts. So since I last spoke at an IUC in 2009, there have been quite a few advancements in the area of improving technological support for African languages at the infrastructural level of encoding, cataloging, transliteration, and enabling input. In the Vai language of Liberia, which has a script in Unicode, encoded in Unicode 5.1, Taha Jaha signifies advancement, or to go forward. Continuing with Vai, two 19th century manuscripts have been translated, and a 180-page manuscript from the early 20th century now has a provisional draft translation. CLDR, or Common Locale Data Repository data, has been uploaded, and fonts are commonly available. Some input tools are available, but more has yet to be done to bring keyboard layouts to their full potential. A Wikipedia in Vai is being incubated, and has articles for subjects ranging from Liberian presidents to Ebola to the theory of relativity. So Vai is one of the encoded scripts of West Africa in Unicode. The rest are listed here: Nko, Bamum, Basava, Mende Kikakwi, Adlam, and Mede Fidrine. This is an example of Ebola public health messaging from 2014, translated into Vai by Tomakai Sherman from a frequently asked question file of the World Health Organization. The Liberian language of Bassa has a script known as Bassa-Va that has also been encoded into Unicode. Font coverage is less commonly found, and only 2 input tools are available to date. Students of Johannes Bergerhausen have worked on font designs, while Richard Ishida and Andrew Cunningham have worked on input tools. The history of Bassa-Va as a script goes back to at least the 1910s, when a young Liberian medical student studying in Syracuse, New York, worked on assembling type for it at a printing company. The language is being taught at Harbel College in Liberia. Here's an example from the Christian Educational Foundation of Liberia of Bassa-Va characters in use as an index to linked terms in a Bassa English dictionary. The Bassa-Va characters are shown on the bottom row. 2 scripts that have found wide cross-border use after originating in Guinea are Nko and Adlam, that are of importance to the Mandé language and the Fula macro language, respectively. These scripts, along with Vai, were useful in supplying public health messaging during the 2014 to 2016 Ebola outbreak that affected West Africa. Both are in use in multiple countries in the region. As with Vai, an incubated Wikipedia was started in Nko, and it now has been graduated into a full-fledged Wikipedia in its own right. This is an example of a map that was produced originally by the UN, but translated into Nko by Baba Mamadi Jane. And here's an Adlam example of Wikipedia. This is the article on Mali. Mende Kikakwi is an encoded script with very limited modern use in Sierra Leone, but it is of interest to scholars and historians. One of the more significant collections of material is a set of 300 notebook pages written by Bokari Kane, a goldsmith who was actively recording notes in the 1950s. This collection was donated to Yale University by Dr. Conrad Tucksher in 2009, digitized, and made available for crowdsourced annotation through the 10,000 Rooms project by 2019. It's housed as MS 2049 in Manuscripts and Archives at Yale. While we don't have a good example yet of the use of Mede Fidrine as encoded in Unicode, we do have an example of the use of the script from its historical context. This is an excerpt from a sample that was reprinted in RFG Adams 1947 in the journal Africa, and represented by Rovenchak and Gibbon et al. In their Unicode encoding proposal from 2016. The script was invented in the 1930s for an artificial language used by a church in the Calabar province of Nigeria. Here is an example of a rendering into Unicode of a manuscript from the British Library. This is an outline of the syllabic repertoire of the Bamum script in its current form, the Aka Uku syllabary. So it begins Aka Uku Ere to O and continues on through the full modern script. It ends with the number for 10 repeated several times. The original is kept in the British Library. It was part of the Bamum Scripts and Archives project. This is a partial list of scripts that remain unencoded from the region of West Africa, including Bete of Cote d'Ivoire, Gare of Senegal, Pele and Loma, both of Liberia and Guinea, Masaba from Mali, various Hausa scripts from Nigeria and Niger, 2 Fula scripts from across West Africa that used to be in use, Dita and Ba, the Ndebe script of Nigeria, the Ki script of Cameroon, and the graphic systems of Adinkra and Nsibidi of Ghana and Nigeria. I'll present here some examples of the use of unencoded scripts in projects that incorporate the handwritten form. So this is a partial excerpt from what will become a Wikipedia in the Bete language, using the Bete script of Frédéric Boisbré, the late Ivoirian artist. And these are COVID-19 guidelines for prevention, also in the Bete script. This is a letter that was written up in Loma, in the Loma script, from Pema Tupu of Guinea in 2020 and sent to me. He says that he'll translate it for me, but I haven't seen it come through yet. I've been able to transcribe about a third of it. And this is an excerpt from a book on animals in the Gare script, in the Wolof language, of El Haj Hassan Faye. This page is about the kakatar, or the chameleon, in Wolof. Then these are some examples in the encode script of how use in libraries has been extended into the library catalogs, both from Yale University on the left here and from Harvard on the right. There are 2 records for the same language, for the same book by Suleiman Kante, and the book is called Jibire Bafasa. So it shows you the potential that we'd like to see happen with furthering the use of Unicode into library catalogs as it develops into the infrastructure of the systems that we use. There's a centralized library database used widely for interlibrary loan called OCLC, which has moved to full Unicode as of 2015. That's up to the version 6 of the Unicode standard, at least, with tentative plans to go further beyond that. The Library of Congress is still, in its authority records, it's still limited to about Unicode 2.0 using the font Arial Unicode MS, but there are hopes of getting beyond that shortly.
Thank you, Deborah, for showcasing the tremendous work that the Script Encoding Initiative has been doing in digitizing the world's writing systems, and to Charles for that amazing presentation on just how far we've come with the digitization of African writing systems and the potential that that holds. Hello, my name is Anshuman Pandey, and I will be speaking with you today about the progresses and challenges of current script encoding initiatives. I've had the pleasure of working with the Script Encoding Initiative for the past 15 years and have had the good fortune within that time to encode 30 scripts, 4 number systems, and 3 emoji. I've also identified and scoped the requirements for encoding an additional 40 scripts. Of course, script encoding is a labor of love, and when I'm not engaged in this labor, I'm working as a senior analyst in marketing analytics and insights at Avant, which is an amazing fintech company in Chicago. Today, I'd like to discuss the challenges and progress of 3 scripts that I'm working on currently. These are Old Uyghur, Proto-Cuneiform, and Proto-Elamite. Some of you here today may have heard me speak about the Old Uyghur script at past conferences, and it's a script that I've been working on for the past 4 years. And even though it's a script that technically has only 18 characters, it has several challenges that have required a lot of investigation, not only by myself, but by the script ad hoc. And we have finally gotten this script encoding model to a point where it is suitable for approval by the UTC. So the Old Uyghur script, for those of you who are not familiar with it, is a script that was derived from Sogdian, and it was used primarily by medieval Turkic speakers in Central Asia. And it also had users that extended all the way to Anatolia, down to Iran and Afghanistan. And it was borrowed into Mongolia, where it served as the basis for the current Mongolian script. It was used beginning in the 7th century for Buddhist and Manichaean religious documents, and eventually emerged as an administrative script that was used throughout that region in the post-Islamic period for political and for just regular administrative documents. Now, there have been several challenges associated with the script, and I will describe some of those here today. Among the many challenges of the Old Uyghur script is a change in its orientation. On the left, you have a block print set in the square script style of Old Uyghur, which shows text in the normative vertical orientation, which is top to bottom, left to right. And on the right, you have a document that is written left to right, horizontally, top to bottom. And this is a style that was used predominantly in the post-Mongolic era. Another challenge in encoding Old Uyghur has been determining the scope of the character repertoire. In early documents, all 18 characters are distinguished to some extent, but by the 14th century, when block printing is introduced, several letters are merged and are represented using a singular form in certain positions. And by the 17th century, several letters are basically indistinct from each other. For purposes of encoding a script in Unicode, such as Old Uyghur, my goal is to enable representation of the largest set of texts possible using a defined character set. And I have tried my best to identify distinctive glyphs to encode as Old Uyghur characters for these 18 letters. And eventually I found that sort of evidence in Friedrich Max-Müller's Uygurica, which was published in 1908. In this document, Max Müller published a square script manuscript using metal type, in which he distinguishes the contextual forms of all 18 letters. So for example, in the top left, you'll see a differentiation between Aleph and Nun, where Aleph is highlighted in red and Nun is highlighted in blue, and co-occurrences of the two letters in medial position are highlighted in magenta. And the same case is evidenced for Beit and Yod, where in the top right you have Beit in red and Yod in blue, and on the bottom where you have Samek and Sheen that are distinguished in red and blue respectively. So using this as a primary source, I was able to work out a repertoire for Old Uyghur in which all 18 letters that are paleographically assigned to the script now have a one-to-one match in the proposed encoding. Earlier proposals also highlighted the usage of diacritics that were used for transliteration of Arabic sounds into Turkic languages. And although these are documented in the primary sources that I've consulted, there are other transliteration signs used in post-Mongolic documents which I feel should be added to the block as well. So I have decided at this moment to table the encoding of what I consider to be late diacritics, so that these and others can be encoded as a set in the future. One other sticking point for Old Uyghur has been the issue of how to handle letters that have terminal variants. I believe that there is a case for representing certain final forms of letters that have different terminals as separate characters for the purpose of representing text as it appears on the page. So for example, you have here Aleph and Nun, where Aleph is in red and Nun is in blue, and the conventional forms of the final letter are shown with the label A and the hooked form as B, as is apparent, while the individual final forms, conventional final forms, are distinct, the hooked forms are not. And so there needs to be additional research performed in order to determine whether there is in fact a need for representing, let's say, forms B for Aleph and Nun, or whether forms A should suffice. At present, these are to be considered glyphic variants, and once the initial block is encoded, I will go back and conduct additional analysis and research on terminal variants. Now, the space-filling terminal, which occurs predominantly with the letter P, has also been tabled. Although this is a sign or character that is suitable for encoding, we do not fully understand its context of usage, and so it's better to table this until additional research can be done. Now, one of the pitfalls of reading a lot of documents is that at some point you become inoculated to certain graphical features and you just take them for granted. And that is the case for me with regard to inter-word terminal connections, which was brought to my attention back in August by Ruzbe Pornader, who asked me if we will need to encode certain special forms of final letters or medial letters to represent interword connections. And for a second, I wasn't quite sure what he was referring to. But when I looked at the examples he sent me, I realized, by God, he's actually onto something here. And what I realized was that there is no true semantic value to these connections. What's happening here is that the scribe is moving the pen whenever possible in order to effect continuous writing and taking advantage of letters that have extensible tails in order to keep the pen moving, to keep the ink moving. So what we see in effect is, in many cases, lines in Old Uyghur documents that seem to have absolutely no word breaks. What is happening, in fact, here is that terminal extension is being used as a space, but also back to the point of keeping the pen moving whenever possible. So looking at the top example here, we notice that there are examples of Yod and Zain and other letters like final, pay, which go vertical, or in the true sense, which go to the left, that do not connect to the following letter. But letters like Nun, letters like Gimel, that naturally have a tail that can be extended, their tails are extended whenever possible. We have decided to add a provision for effecting such connections if users prefer to use the terminal extension instead of a space by using the zero with joiner character. So now for Old Uyghur, the next steps are to get final review by the script ad hoc, which I believe is taking place on Monday. So I hope that the most recent proposal is reviewed positively by them, and then after that, the next step would be approval by UTC. However, as is the case with most scripts that I work on, once the script is encoded, I'm not really done with it. I am going to go back and identify all diacritics that occur in late documents, and then consult with experts on the representation of terminal variants, and then also look into the usage of additional punctuation that occur in the script. Now, some months ago, Deborah asked me if I had any interest in working on Proto-Cuneiform and Proto-Elamite. And when she asked me, I was absolutely ecstatic at the opportunity of encoding in Unicode two of the most ancient, if not the first, attested writing systems in the world. And these are what is shown on this slide under Mesopotamia as pictographs, which I will call here Proto-Cuneiform, and extending to the right here, Proto-Elamite pictographs. Now, Proto-Cuneiform is the first attested writing system in the world. It was used in Sumeria beginning in the 4th millennium BCE and consisted entirely of pictographic signs that were used for recording administrative and economic records. We still don't know what the underlying language is, but based on comparisons with later cuneiform and with numerical systems, scholars have made a lot of progress in identifying what the underlying values of the signs are. The primary challenges for encoding proto-cuneiform have to do with identifying what the full suitable repertoire might be, how to handle alternate forms of letters, and how to handle complex signs and complex. So here we have one tablet of proto-cuneiform, which on the left depicts an account of barley provisions, and on the right, on the obverse face, has graphical images of animals. And here we can actually see the true difference between images and actual linguistic or semantic usage of signs in an ordered fashion, or what we would call writing. So here is a tablet that describes beer rations, and we see uniform usage of signs throughout the tablet. So here we have a sign called Kosh, variant A, which represents beer, and we have a black dot which represents a form of the number 1 that is used in capacity systems, and we have a sign on the bottom left hand which indicates to eat. So we have discrete signs that are ordered and that have uniform shape that are used consistently throughout a text. And this gives more credence to the fact that what we're dealing with here is a true writing system, not just representation of images or some sort of painting. These pictographic signs represent concepts, objects, people, animals, processes, and numbers. And we have more evidence that this is a true writing system because the text is ordered. Here it's ordered in columns with signs for a particular object represented on the left, followed by a numerical notation on the right. And then we also have a header. So that header, GU variant 7, which is believed to be the sign for to eat, is here used as the header for this tablet. And in this context, that header represents a ration. So we understand here that there are a number of cases of beer being given to some person or to some group or some institution. And this here tablet is a record of the distribution of that good to those individuals. Proto-cuneiform is also believed to be a true writing system because it has a formal numerical notation system. Not only one, but it has 6 notation systems for objects, 6 for capacity systems, and 1 for time. And what is interesting is that there are certain numerical signs for certain values that are used across the systems. And the way in which the system is differentiated from another is by the ordering and by which sign is used in a positional context. The proto-cuneiform is used also by scholars in running text. Now, this is one of the main rationale for determining whether or not to encode these characters in Unicode. Is fine, we understand that these are distinct signs that belong to the very first writing system produced by humans, but are they used as text or are they used as images? And here we have an example where the proto-cuneiform signs are in fact used as text, not only by reference to the names that are given to them by scholars, but by usage of the actual character and its glyph within running text. When I first started working on proto-cuneiform, I reviewed the documents that were submitted by Everson and Hawkins, and then turned to producing an understanding of the script on my own accord. And I first used the sign list that was compiled by the late Professor Robert Englund, who contributed his sign list to the Cuneiform Digital Library Initiative. And his sign list identified 2,095 characters. And I took his sign list and did some extensive analysis and produced a typology of the signs for Proto-Cuneiform. And this is a breakdown of the signs in terms of complex and individual signs, and then subtypes of those two classes. The 640 complex or compound signs of Proto-Cuneiform are typically broken down into numeric and ideographic signs. But for purposes of character encoding, I wanted to get a better sense of what the underlying structure is for all of these signs. So I did some additional analysis, which resulted in this typology here, which shows the pattern of formation used for what I consider 4 subtypes of compounds, which I distinguish as numeric, ideographic, numero-ideographic, and idionumeric. And in this pattern, a multiplication sign indicates that the sign is embedded within the preceding sign. A plus sign indicates that the preceding sign is joined to or fused to the following sign. An ampersand indicates that the preceding sign is stacked vertically above the following sign, and a dot indicates that the preceding sign is placed beside but not joined to the following sign. Now, the challenges that I am encountering with Proto-Cuneiform have to do, on one hand, with identifying and understanding glyphs that have similar representations and how to consider these in terms of encoding. Now, are these variants or are they alternate forms? Like, let's take the character right in the middle, Gu7. So Gu7 has one form in which the bowl is right below the chin and one where it's below the neck. And these occur contrastively in tablets. And so for representing those tablets, for as text appears on the page, would we consider these as separate characters, as distinct characters, or would we unify them as glyphs? If we look at the case of Dub, variant B, we see that Dub has a structure that is either a square base or a circular base, which is hatched, and the two lines can have a connector to the left, or they may not. Now, how many of these signs need to be represented individually or not? This is a question that I need to follow up with experts upon, and with their help, we'll be able to identify whether these forms of Dub are true variants or whether some of these should be considered alternates. The same is the case for Gan and also for Shen. Another challenge is the representation of compounds. So there are 2 ways of approaching compounds. One is to encode all the compound signs as atomic characters, or to decompose those which may be decomposed. Now, the question with regard to the second approach is, how do we determine which characters to in fact decompose? Now, do we decompose a sign like Ninda2, which embeds on into 2 characters? And if so, do we need some sort of formatting control character as we use for Egyptian hieroglyphs to effect the joining of those 2 as a single compound? For gear, it may be as simple as decomposing this compound and placing two signs of gear next to each other. But then, do we need to effect the overlap of the fins for this compound? And similar question for the gi over gi. If we were to just simply decompose this and put into place a character that would control vertical stacking, how do we in fact control the positioning of these characters as well? So determining which compounds to decompose, and in fact, if we need to decompose compounds for proto-cuneiform, is a great challenge that needs to be resolved before the script can be adequately encoded. Another challenge is determining names for the characters. So there's a precedent set for character names using the Sumero-Akkadian pattern, where the multiplication sign is transliterated as times. Now, however, that sounds a little colloquial to me. It does not actually represent the function of an operator for proto-cuneiform, where in fact that multiplication symbol represents an embedding of one character within another. And in terms of characters like the ampersand or period, or in terms of grouping, we need to understand what would be the best way to represent these sorts of compounds that not only adheres to the Unicode naming convention, but also adheres to a convention that is acceptable to scholars who would use these characters. Now, on the left here, we have a small chart that shows how proto-cuneiform letters developed into later cuneiform. And over here on the right, I have another progression that shows proto-cuneiform signs evolving into later cuneiform signs and extending further into more modern, very highly pictographic. So my question is there a return to pictographic expression now that we are moving forward with encoding emoji? Now, the next script I want to talk about is Proto-Elamite, which was used in Elam, a region just east of Mesopotamia in current modern-day Iran, which is also highly pictographic, but it has no attested descendants at all. It too was used for administrative and economic purposes, and it has not been fully deciphered, and the underlying language itself is not known. And the primary challenges for encoding this script is determining the character repertoire and also identifying the pattern for encoding complex signs or compounds. Now, the region of Elam was introduced to me very early on as a student of history, but it was imprinted upon my mind with a lot of force when I read Ted Chiang's Tower of Babylon many years ago. In that short story, we have a case of a builder from Elam going to Babylon in order to work on the tower, and at a very crucial point in the story, the builder refers to a seal cylinder, and this is what we see here: a cylinder that is carved such that its opposite ends produce different representations when they're rolled out, but they connect on the cylinder itself. And this was a very potent metaphor for me. And when I started working on Proto-Elamite, I remembered the story, and I went back a few months ago and reread it, and it still held the same poignancy today as it did for me many years ago. And it actually really inspired me to work on Proto-Elamite even more. Proto-Elamite is also pictographic writing, and we have here a tablet that shows both actual writing as well as what I would just consider art or graphical images. So at the top we have pictographic signs that represent numerical notations in a decimal system, as well as a sexagesimal system and a mixed system that's used for capacities. And then in the middle, throughout the clay tablet, we have two seal impressions made of the same seal, showing images of a bull symmetrically restraining two seated felines, alternating with a lion dominating two rearing bulls. So a very strong example of the differentiation between writing and between graphical representation within Elam itself. There have been a lot of scholars who have done amazing work on expanding Proto-Elamite studies, and one of these individuals is Laura Hawkins. And here we have a tablet upon which she's done a lot of research. This is a tablet from the Louvre, known as 17,112, and the CDLI has been absolutely phenomenal in terms of making Proto-Elamite materials available to the public. And on the left, we have the actual high-resolution image of the tablet, and on the right, a very important and very informative drawing of the signs. So if we were to actually have to rely on the resolution and of the clarity of the tablet itself, it would be very hard to distinguish to the untrained eye what symbols and what signs we're dealing with. But through the help of Laura Hawkins and the folks at CDLI, we can work with tracings, which is an absolute blessing for people working on Proto-Elamite. So Proto-Elamite is a writing system, and a true writing system at that. So here we have various signs, and as I mentioned before, this script is not fully deciphered, so we have a tentative understanding of what the signs represent, and this is partially based on comparisons with Proto-Cuneiform. Although the two scripts are not fully related, they do share a common numerical system, which has aided in decipherment of Proto-Elamite. So here we have a sign, and the sign names here are all prefixed by the letter M, which refers to a list produced by Paolo Merigi in 1971. So we have a compound sign at the very top, then we have another sign, M317, and then we have numerical signs. So we have in Proto-Elamite a differentiation between numerical and ideographic signs, and a whole slew of pictographic characters that represent concepts, objects, people, animals, processes, and numbers. There are at least two decimal notation systems that were used in Proto-Elamite. And we see here in the first two rows the two different notations, most likely used for capacity and for objects, and potentially a third, but for which we only have the values 1 and 2. Now, Proto-Elamite is also used by scholars in running text. And here we have examples of Proto-Elamite signs used in descriptions of rations. And this is important for character encoding because here we see signs being used as text and not only as images. Now, the Proto-Elamite repertoire consists of 1,636 signs. And these are also broken down into general ideographic and numeric signs. And within the general signs, there are compounds that can contain either 2 or 3 signs, which are further differentiated into complex capacity signs or complex graphemes. And a complex capacity sign is used for counting objects such as jars, pots, etc. And there are 3 common bases shown down at the bottom of the slide that are used for complex capacity signs in Proto-Elamite. And a complex capacity sign is defined as one numerical sign followed by other non-numerical signs or more than one numerical sign inscribed within the frame of a non-numeric sign. And a CCS that contains a numerical sign likely indicates a quantity of the product being expressed, while a CCS with a non-numeric sign likely indicates a quantity of the product. Now, there are several types of complex capacity signs, some of which are shown here. And then there are complex graphemes, which are used for counting inanimate objects such as persons, households, and other quantities. And I have done an extensive analysis of the types of complex graphemes, and there are at least 3 with some subtypes, and these are described on these slides here. Now, for example, type 1 is a compound which is represented by having 2 instances of one sign that vertically frame another sign. And as part of my research on the script, I've identified 17 signs that appear in compounds, but which do not have independent attestations. Now, one of the biggest challenges for encoding Proto-Elamite is the encoding of compounds. Just in the same way as for Proto-Cuneiform, so for Proto-Elamite is, do we encode compounds atomically, or do we find a way to decompose them? And if we do decompose them, do we use format controls to enable vertical stacking, the embedding, the mirroring of glyphs, and how do we control for embedding certain glyphs in certain specific locations of another glyph? The projects to encode Old Uyghur, Proto-Cuneiform, and Proto-Elamite were supported in part through a grant from the National Endowment for the Humanities to Dr. Deborah Anderson and the Script Encoding Initiative. All information I've expressed here is my own and does not reflect any position of the NEH or SEI. And thank you. Please do get in touch. I can be reached via these channels. And cheers. Thank you for taking the time to attend our session, and best of health to everybody. Thank you.